Hi, I'm David Dodge. Welcome to Green Energy Futures. Heating buildings is responsible for 30 to 40% of greenhouse gas emissions. And it's one of the biggest nuts to crack as nations move to net zero emissions. Just about every single climate and energy transition plan says we must move to use heat pumps to eliminate emissions from buildings. But what is a heat pump? How does it work? And how can it help me save energy and money in my home? We sought out an expert to walk us through the magical mystery workings of heat pumps.
Hi, my name is Jean-Marie Robert. I'm an instructor at NAIT in the Alternative Energy Department, where I teach geo-exchange systems and high-performance buildings.
Jean-Marie is a physicist. He's standing beside a model air source heat pump. We asked him to give us the lowdown.
So this is something that I spend semesters worth of work with my students to go into detail. But in essence, a heat pump is just a machine that will basically reverse the flow of natural heat flows. So for example, what we have over here is a mock-up of a air-to-air heat exchanger. And what we see is a simulation of what we would have in the outside and what we would have inside the house. So just like a regular air conditioner, you have an outdoor unit sitting on the side of your house, which interacts with the atmosphere on the outside. And we'd have an indoor unit, which would be located in your plenum, or this could even be a self-contained unit right inside your house to deliver the heat or the cooling, depending on what you're trying to achieve. The way the heat pump works is quite simple, even though it looks quite complicated. But what we have is a refrigerant inside of these copper tubes, and this refrigerant just flows around in circles and never leaves the system. The only thing that gets exchanged is the heat from one medium to the other. So let's take this as a heat pump in heating mode where we're trying to heat the inside of a building. So this building would be held at, let's say, 20 degrees Celsius, and the outside might be something like minus 10 degrees Celsius. So our objective is to take the heat from this room at minus 10 and put it in this room at plus 20. Which seems the opposite of what it wants to do, because it is in fact the opposite of what it wants to do.
It's quite bizarre. We want to heat our plus 20 degrees Celsius home with heat extracted from the minus 10 degree air outside. It turns out that heat just naturally wants to flow from hot to cold areas. So the heat pump actually chills the fluid to minus 30 before sending it to the minus 10 degree air outside.
So let's start from the outdoor unit. We want to bring the heat again from the outside to the inside. So we need to be able to take heat from minus 10 degrees Celsius and put it inside these coils. So the heat pump will hold these coils at a temperature of something like minus 30 degrees Celsius. So the heat will naturally go from the minus 10, which is relatively hot, to the minus 30 inside the coils. So this cold refrigerant flows back into the compressor down here, where the compressor essentially just increases the pressure and increases the temperature of this refrigerant that flows onto this side. So once it passes the compressor, the coils are going to be at around 50 degrees Celsius. So 50 degrees being higher than 20 degrees, the heat naturally goes into the space. So we're able to heat this space with that. And then we have to repeat the cycle. So when it comes out, we go through this little metering device here, which will take the high pressure, high temperature, drop it back down, and take this coil back to our cold minus 30 temperature. And then the cycle continues. So basically, we are just taking heat from the cold air and putting it into the hot house.
The model is an exploded view of an air source heat pump. Broadly, heat pumps either extract heat from the air or from the ground, so-called geothermal systems.
So the air source heat pump, what we saw earlier, was where the outside unit is interacting with the air above ground, which has a lot of temperature fluctuations, which makes them a little bit less efficient. In this case, we have a geo-exchange unit, which looks a lot like your home furnace. And what it does is it takes the energy from ground loops. So we have some loops that are into the ground, and we can grab some thermal energy from it or dump energy back into the ground. The loops then send energy into our heat exchanger inside of here. It looks exactly the same as our previous example, and then would release the energy or the heat through a plenum, just like your home furnace. What we have over here is a mock-up of the same exact heat pump, just to show us what the internals look like and also show the students how the heat pump would work. Down at the bottom here, we have a reservoir, which would represent the ground itself. The water that we have in here would be at around 5 degrees Celsius, which represents the ground temperatures here in Edmonton. The water would then come into the heat pump up in this area here, and then go through a heat exchanger that looks exactly like this one here. So this is a coaxial heat exchanger that will take the energy from the water and put it in a refrigerant. The refrigerant, just like we had before, would be at a temperature that is colder than this loop. So let's say the refrigerant's at minus 5 degrees Celsius, the water's at plus 5, the water's actually heating up the refrigerant. Once we've gathered some energy from this water, we go through a compressor at the back that we can't quite see, and the compressor will upgrade that heat again and send the refrigerant up in this area here, where this is our water to air heat exchanger. The refrigerant is going to be at about 40 or 50 degrees Celsius. The air would come in through this unit using a blower, which is identical to what you have in a normal furnace. And the air at 20 would absorb energy from this heat exchanger, which is at plus 50, and come out the top at something like 40 degrees Celsius, thereby heating your house. One of the great advantages of these heat pumps is that they're not just a one-use thing. Your furnace only heats your house, whereas this thing can be used for more than that. We can heat up our house. What we have over here is a hot water tank. We can simultaneously heat up our water for domestic hot water using something called a desuperheater. And this thing also has a reversing valve that we can flip in the summertime to provide our cooling. So instead of having a furnace and an air conditioner, we can use the heat pump for heating and cooling and even provide us with domestic hot water.
So one system provides you with hot water, home heating, and even air conditioning, which is something people are looking for increasingly in Canada these days, thanks to climate-induced heat waves. Heat pumps are not new. You have one in your fridge, your freezer, and air conditioner already. Indeed, there are more than 100,000 ground source heat pumps installed in Canada already. One of the biggest reasons we're talking about heat pumps these days is they use very little energy.
So if you want to heat your house with, for example, a space heater, an electric space heater, what ends up happening is every unit of electricity you put into them, they will put out 1 unit of heat. So for every 1 unit, you get 1 unit. We call that 100% efficient. A heat pump will do something different. For every 1 unit of electricity, it's able to absorb free heat from the outside and transfer it back to the inside. So for every 1 unit of electricity, we're able to get something like 4 units of heat back into your house. In cooling mode, it's even more efficient. We may be able to get 7 units out of your house for every 1 unit of electricity. We call that 700% efficiency.
At scale, heat pumps are revolutionizing heating systems. A church and social housing project in Edmonton, Alberta has one ground source heat pump system that heats 16 units and a church with no gas utility bills. The Salvation Army's new 175-unit complex, also in Edmonton, will save $240,000 a year on utilities by using a ground source heat pump. Saving money is one thing, but it's also one of the few proven ways that we can heat buildings and produce no emissions.
So as it stands, the heating and cooling of buildings consists of about 30% or 30 to 40% of our energy consumption. And in the residential setting, your utility bills, almost 80% are heating and cooling and domestic hot water. We have a great solution with heat pumps which it can provide all the heating, the cooling, and the domestic hot water you need in an electrified setting. And in a quest to net zero, it's really the only viable solution we have to get there. What it will do is let us produce on-site electricity using solar panels, for example, in order to heat, cool, and get all our energy services that way.
It seems likely that heat pumps and geothermal systems are poised to become the key method of heating our homes and buildings in the future. Although it can be challenging getting good advice and to source knowledgeable suppliers, this is changing too as traditional HVAC people learn about the technology. Air source heat pump systems tend to be more affordable, but they must deal with the wild temperature fluctuations between minus 30 and plus 40. Ground source heat pumps are more expensive, but They're also very efficient, especially in cold climates. Business is up for geothermal companies installing systems in single-family homes, but the economics are amazing for multi-family complexes. Thanks to Jean-Marie Robert of NAITs Alternative Energy Program for this heat pump primer. Check out our blog at GreenEnergyFutures.ca for more details. For Green Energy Futures, I'm David Dodge.